All right, let's dive into this. So you guys were introduced to logs last year. Do you guys remember liking logs, or were you indifferent to logs? Were you like, these things are the worst things ever? Why would anybody ever invent this? Logs are super, super useful. They come up a ton in the scientific world when you have to deal with things that are really, really big or really, really small. They're very, very useful to us. And they're also useful as a tool for solving equations. We're going to be using that a lot when we get to equations in our last section. That'll be after Thanksgiving. So hopefully after today, we kind of get a better idea of what logs are. But the main key, if you can remember this one thing, it'll make your life a lot easier. Logs are exponents. When I ask you to find the log of something, I'm asking you to find an exponent. So a log is an exponent. And if you can remember that one little fact, that'll get you unstuck from a lot of sticky situations. It's also super useful to us because if we know our rules for exponents, then those automatically translate to logs, right? So do you guys know when do we add two exponents together? Can you think of a situation? Can you create a problem where you would add two exponents together? I hope you can. That same situation would apply to adding two logs together. So logs are exponents. So today we're not going to worry about all those properties. Today we're just going to try and wrap our heads around what logs mean, and then just look at a couple ways to either translate between logs and exponentials, and some ways that logs and exponentials can cancel each other out. They're inverses of one another. So here we go. If I asked you to find me the exponent, you'd stick onto a 3 to make it equal to 9. You guys could all do that, right? Without even thinking. It's a 2. Spoiler, it's a 2. Asking you that question is equivalent to asking you the question, what is the log base 3 of 9? When I ask you to find the log base 3 of 9, I am asking you to find the exponent. You'd stick onto a 3 to make it equal to 9, and the answer is 2. All right, what's the exponent you'd stick onto a 2 to make it equal to 16? 4. An equivalent question would be, what is the log base 2 of 16? When I ask you this, I'm saying, what exponent can I stick on this base of 2 to make it 16, and the answer is 4. See what you guys can do with the next couple ones here. All right, what's the log base 5 of 1 over 25? That would be the exponent that I'd stick onto a 5 to make it equal to 1 over 25. I think it's going to have to be negative, right? Negative 2. So the log base 5 of 1 over 25 is negative 2. What would I put onto a 10 to make it equal to 10,000? Count the zeros. That would be 4. Because there's 4 zeros there. So log base 10 of 10,000 is 4. This one's a little tricky. I've got e to the x times e to the 5th. If I wanted to write that with just a single base, what are we going to do with these two exponents? Add, subtract, multiply, divide. We should be adding them. We practiced this a little bit last class, folks. I need you to know your properties of exponents. When we come back from break and we're doing properties of logs, they're going to be very difficult if you don't know when do we add exponents. All right, so then the log base e of e to the x times e to the 5 is x plus 5. I'm going to skip this little table right now and go down to the bottom here. So let's evaluate some of these things. So I want you to be able to look at the log base 2 of 8 and know that what I'm really asking you is, what's the exponent I'd stick onto a 2 to make it equal to 8? And the answer is what? 3. 2 to the third is equal to 8. So the log base 2 of 8 is 3. Right. Log base 5 of 125 is what? That would be the exponent that I'd stick onto a 5 to make it equal to 125. What power could I stick onto a 5 to make it 125? Is it 3 again? That's boring. So the log base 5 of 125 is 3. The log base 7 of 1/7 is just the exponent that you stick onto a, remember the base is the thing that you're putting your exponent onto. So we stick onto a base of 7 to make it equal to 1/7. And that exponent is -1. 7 to the -1 power is 1/7. So I'd like you guys to just run through and practice a whole bunch of these. I want to remind you that there are a couple special logs. One of them is called the common log. If you ever see a log that does not have a base written, you guys know that that base is meant to be what? 10. And why is 10 such an important base? Because we count in base 10. Do you guys know why we count in base 10? Don't say because it's easy. This is a historical thing. Nobody knows for sure, but why do you think we count in base 10? It's not because it's easy. It's easy to you because you learned it that way. If you'd learned how to count in base 8, it would be really easy for you also. There's a physiological reason, probably, that we count in base 10. What do you think it is? What do you learn to count on when you're a little kid? Yeah, 10. You got 10 fingers. That's probably the reason we count in base 10 is because you have 10 fingers. Do you know that there are cultures out there that count in base 12? You want to know how that works? Have you seen this before? This is how you count in base 12. You count the segments on your fingers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So some cultures count that way. And it's kind of nice because you can count up to 24 with 2 hands. In some cultures, their number system is in base 12, and you might think that that sounds difficult, but for them it's not difficult because that's the way they do their numbers. So, anyways, all right, enough of history, archaeology. Let's see what you guys can do with these. I forgot to talk about ln. ln is another special log, and when you see ln, it's the log with a base of e, and this comes up enough that they have shortened it. ln stands for, do you guys remember what it stands for? Natural log. And why is it ln and not nl? Natural log. Because why? Log natural, yeah. Because French. Right? Any of you take French? I think it's the same in Spanish too. How do the adjectives work in Spanish and French? Like, you don't say the red ball, you say the ball red, right? It's not the natural log, it's the logarithm naturel. But I'm pretty sure it was a French person who came up with it. So, more history. Isn't history great? All right. These last 3 kind of illustrate one of the cool properties of logs, and is that logs and exponentials are inverses of one another. It says that they cancel, but let's make this a little bit better. That means they're inverses. And you guys remember how inverses work? Remember we talked about there was a machine that took cows in and spit out cheeseburgers, right? And then there was the inverse machine that did the opposite, took cheeseburgers in, spit out cows, right? And what happens if just for fun we decided to put them like back to back and have one feed into the other? We stick a cow in, and what comes out the other end? A cow, right? It's a cheeseburger in the middle. It's a very confused cow, right? But whatever I put in here, I'm going to get the same thing out here, because that's how inverses work. They basically, it undoes, this one does something and this one undoes it, and we get back to where we started from. So that's what's going on here. I got an exponential with a base of 5, and I have a log with a base of 5, and since those things are inverses, the thing that I put in is going to be the same thing that I get out. So we think about them canceling. That's kind of a convenient way to look at it, but what's actually going on here is that they're inverses. Exponential base 4, log base 4. Since those are inverses, then my input 3 is going to become my output. E and ln both have the same base, so in order for this to work, the bases have to match. Right? And E and ln both do have the same base, so they're going to cancel, and we'll get 7.2. Ooh, this next one's tricky. We got to know some exponent rules to make this next one happen. I can't do anything with this because I've got both a 2 and a log 5. I want my 5 to just have a log 5 on it. Can you think of a way I can separate it so that I write this with 2 bases that are separate? When do we add exponents again? When I'm multiplying 2 things. So if I'm multiplying 2 things, then I would add the exponents. What would be the 2 things that I'm multiplying? They're both going to need a base of 5. One's going to be 5 to the 2, and one's going to be 5 to the log base 5 of 3. We all know what 5 squared is, right? And what's 5 to the log base 5 of 3? 3. So the final answer is 75. Oh no, what's going on here? My bases don't match up. This is a 2 and this is a 4, and then there's another 2 sitting out here. Bummer. When do we multiply two exponents? That's what I see going on here. I got 2 times this log. When do we multiply 2 exponents? We multiply 2 exponents when we've got a base inside and there's exponents on the inside and outside. My base would be a 2, and then my exponents on the inside and outside, one would be a 2 and one would be a log base 4. And this ends up just being 4, right? So that works out nicely. Final answer of 3. Ooh, this one has subtracting exponents. When do we subtract exponents? When we're dividing, right? So if I were subtracting exponents, we'd have a base on the top and a base on the bottom. And my base up here is log x, and my base on the bottom would be a 1. That numerator just becomes an x because the base and the log match. Denominator is a 10. X over 10. Are we okay on exponents? I'll tell you what, guys. We did exponents in Algebra 1 the last 3 classes, and I recorded those notes. I will put those on. I'll put a link to that on our Canvas page just in case anybody needs to review. When do we add? When do we multiply? When do we subtract? And then the third video is negative exponents, which we will run into a little bit here. We skipped this up here, but I think we've done enough practice with that. So you can use that for some extra practice if you like. Let's move on. All right. Relationship between logarithmic and exponential equations. Mrs. Malpass, how many of you had her last year? She calls this the circle of success, maybe? Is that it? The circle of success? Do you guys remember the circle of success? I don't really know how the circle of success works. Does somebody want to explain the circle of success? I know it has to do with bases, like there's bases, and the bases kind of go in a circle. I don't really know. Okay, well, if you know the circle of success, I'd love for someone to teach it to me because it would be cool to be consistent. But here's the basic idea. If I've got an equation that looks like that, then we can convert between a log and an exponential equation. This is going to be one of the strategies that we're going to use to solve equations later on. It's also just helpful to do sometimes, depending on whether you're looking at a value or you're looking at exponents. So here's how I remember how everything works, okay? The way I remember it is that both of these have a base. We know, you guys know how to spot the base on a log, right? It's the little number that's underneath it. And you also know how to spot the base on an exponential. So they both have a base. Whatever the base on your log is going to become your base on your exponential. And then the other thing I remember is that they both have an exponent. Now this exponent is going to be easy for you guys to spot. You've been messing around with exponents for a lot of years now. The thing that I really want you to focus on today, remember this is the first thing we wrote in our notes at the top of the page before. Do you guys remember what that was? What are logs? Logs are exponents, right? So the log is an exponent. Can you guys see that in the equation? The log is equal to an exponent. This thing over here is always going to be your exponent in a log equation. And then the A part, that's the leftover piece. So that's how I think through these. As I remember, a base is a base and an exponent's an exponent, and the other thing just goes in the other spot, right? Circle of success, did it have something to do with like the B came over here and it bumped the C up and that became an exponent? And then we circled back, this B would come over here and it would become the base. Was that your circle of success, something like that? If you remember that and that works for you, go for it. Go for it. I'm gonna do it based off of what's the base, what's the exponent. So when I look at this, let me go ahead and get this set up. I know that it's going to be something equals something to the something power. All right, so look at that equation on the left and tell me what is the base in that equation. The base is 2, right? That log has a base of 2, so I'm going to put 2 as the base in my exponential. And look at that log equation and tell me what's the exponent. Remember, the log is equal to the exponent. A log is an exponent, so 16 is the exponent. So that equation would say x equals 2 to the 16th power. I think in your circle of success, you would take this 2 and it would come over here and it would bump that 16 up and the log would go away. I'm pretty sure that's how the circle of success works. All right, let's try another one. We're going to have something equals some base to some exponent. So what's my base? My base is 5. What's my exponent? Remember, the exponent is equal to the log. So I'd say my exponent is the x. And 42 is the other piece. All right, see what you can do with the next couple. If it helps you just to write in the invisible base, go ahead and do that. And then try the ones on the other side. It's kind of the same thing, but in reverse. So I'm going to start at the top of the other table. If you're not quite done with the table on the left, that's okay. Focus on the table on the right for right now. Same idea. We're going to write a log equation. It's going to be log. There's going to be some base down here of something equals something. So just ask yourself the same question. What's the base? The base is a 6. What's the exponent? The exponent is an x. Remember, a log is an exponent. And then that means the 1,000 must go here. So log base 6 of 1,000 equals x. So give those ones a try. That last one's a little tricky. That'd be one way to do it. There's another answer that some of you might get for this one. Base 2 of 11 equals 2 plus 3x would be another way to do that. For those of you who like the circle of success on these, I think you always try to get it so that the exponential is on the right, I think. And didn't we circle it back here and that became the base on the log? So the two would come over and become the base on the log, and then the x would drop down. I think that's how that worked. No, maybe? Does that look familiar to you, those of you who had this is Malpass last year? Mr. Skaggs didn't do the circle of success, did he? How did he do it? You just learn where the bases went. Yeah, and that's good. I mean, that you want to be able to do it quickly, right? And sometimes the first time you learn something, it's like the best way to do it is just to sort of memorize your way through it. Is it kind of making sense though why why it is the way it is. We have a base in both forms, right? So if you can identify what's the base, whether it's in this form or this form, then you know where that thing goes in the other format, right? If you can identify what's the exponent, and this is probably the new piece for you, right? Is that a log is equal to an exponent. I want you, every time you see an equation that says log of something equals something, if you can say in your head, oh, a log is an exponent, that's going to help you remember that long term. That's going to help you out when we get to our properties after Thanksgiving. All right, any questions on those? Are we okay with why I had to divide by 4 here so that we just had a base? Because we had some extra stuff there. Do you guys see where this answer would come from? If I go back to my original, I had 4 times 2 to the 3x equals 11. I could have rewritten that as 2 squared times 2 to the 3x equals 11, right? And what do I do with my exponents when I'm multiplying 2 bases together? Add them. Are you seeing where that came from now? My base was a 2. My exponent is 2 plus 3x, and there's my 11. Okay, our favorite thing, logarithmic graphs. I bet this means that we're going to get some problems in our assignment where we've got to do the little table thing and like transformations on them. Yay! You guys do not seem nearly excited enough for this. All right, well, logarithmic graphs, they look like this. Those are your basic points. Oh wait, that's not logarithmic, that's exponential. We already did this one together. I saved us some time and I copied all this. This is what we did on our first page of the notes. Do you guys remember doing this? And there was an asymptote. It didn't show up on the graph really well. Can you guys draw that asymptote in for me, please? This is the graph of 2 to the x. If you look at the very first page of the notes, we made a sketch of this, and then we used this as a parent function, did some transformations on it. So we're going to do the same thing with the log base 2 of x. What's significant about these two functions? They're inverses of each other, right? They're inverses. And what happens to x and y values when we take an inverse? X's become y's and y's become x's. That's the big concept of an inverse, right? Inputs and outputs switch. So if this graph had a point at negative 1 comma 1/2, then this one's going to have a point at 1/2 comma negative 1. If this graph had 0 comma 1, then we'll have 1 comma 0. If this had 1 comma 2, then we'll have 2 comma 1. And my asymptote y equals 0 is no longer going to be y equals 0. It's now going to be x equals 0. So logarithmic functions actually have a vertical asymptote at x equals 0. And if we plot those points, we're going to see what the graph looks like. All right, let's do a little analysis here. What's the domain of that graph? There's no negative x values on this thing. Do you think it's ever going to actually hit that asymptote? You're right, it's not. So it starts at 0, gets really close to 0, but doesn't quite get there, and goes to infinity. How about the range? We got some negatives, we got some positives. Do you think we're covering the whole negative to positive range here? We are. And that's good, right? Because what should happen with domain and range when we take an inverse? They should flip-flop. So that makes me feel good about that. We got an intercept. It's a y-intercept. I'm sorry, it's an x-intercept this time, 1, 0. Asymptote is now x equals 0. The exponential was increasing. Is ours increasing or decreasing? Is our log increasing or decreasing? It's increasing. It's increasing, but not over all real numbers. It's only increasing on its domain, so from 0 to infinity. There's no jumps or breaks in our graph, so it's continuous. Bounded above, bounded below. Negative, not bounded. I'm not seeing any symmetry. End behavior. This is kind of interesting. I see an end behavior over here, but what about on the left? Is there an end behavior on the left? Remember, end behavior describes what happens to the graph if you go way off towards negative infinity. Do we even have any graph off towards negative infinity? So we would not talk about the left-hand end behavior of this. It only has end behavior on the right. So my end behavior on the right, folks, this notation for end behavior, this limit notation, I didn't decide this, okay? But this is the way these are written, okay? Some people lost points on the test because they're inventing their own way to write limit notation. So please stick with the convention. It's a little limb. X with an arrow goes underneath the limb. F of x goes off to the side of it, okay? It needs to be written like this. You guys don't have creative freedom to decide I'm going to stick the limit underneath here or just write it all on a big in two rows or something like that. It needs to be in this format. What is my end behavior doing on the right? Up, down, or leveling off? It's up. Yeah, it's going to go up forever and ever. So positive infinity. Now, it turns out the further out we go, the slower it goes up. Like, it's going to go incredibly slowly upwards, but it will always march upwards towards infinity. We could talk about what's happening at this vertical asymptote. This would not be end behavior. So let's label this as end behavior, but we could talk about the behavior at the vertical asymptote. We practiced this last chapter with vertical asymptotes. Do you guys remember how we did that? It also uses limit notation. I'm not going to put infinity or negative infinity with that x. What am I going to put? Where is the vertical asymptote? At 0. And then we put a little plus or a minus on that 0. We can only do 1 in this case. We put a plus or a minus on it. A plus. Which means we're looking at what happens at the asymptote just to the right of it. The plus means to the right. There's nothing going on to the left, so we would not have a little negative version of this. Again, it's always f of x. It's written a little bit bigger and to the side of this, not above it. And then equals 2. And what is the y value as we approach this asymptote from the right? Where's the y value going? Say it's going down to negative infinity. All right, so we're not going to do an example of this, but it says down at the bottom of the page, you should be comfortable graphing something like this and starting with your parent points up here, showing me the tables for these points. We've done this so many times at this point, I feel like you guys would be okay with it. really quickly though, if it says log base 4, let's talk about what our parent graph would be. So if I were doing log base 4 of x, remember I always want you to have 3 points. Do you guys remember the special important x coordinates that we usually use? -1, 0, and 1, except for logs, those are going to become y coordinates. So it's still going to be -1, 0, and 1. All right. So the log base 4 of something is -1. It may help you to think the other way around. 4 to the x power. So if I put in 4 to the -1 power, that's 1/4. So 1/4 goes here. 4 to the 0th power is 1. So 1 goes here. And 4 to the 1st power is 4. So 4 goes here. So if I were doing log base 4, it would look like that. Basically, whatever your base is, you're going to have 1 and that base and 1 over that base. Those will be your parent points for these. Okay. All right. Any questions? I think that's all we got for today. Let's see. Yep, that's what we're going to do when we get back. Questions? Preview, what we're going to do next is log properties. Once again, if you know your exponent rules, then these are going to be simple. Okay, so the product rule relates what happens when you have multiplication on the inside. And if you know that with exponents, when you're multiplying exponents, what do you do with your, when you're multiplying bases, what do you do with your exponent? You add them. So you're going to be able to link this situation to adding 2 logs. We add the exponents, and a log is an exponent. So we're going to be adding 2 logs here. In a situation where I'm dividing 2 bases, what do you do to the exponents? We subtract the 2 exponents. So in a situation where I'm dividing here, I'm going to have 2 logs that are going to be subtracting from each other. So if you know your rules for exponents, then the rules for logs are going to follow from that. And this is going to go pretty quickly for us. And then we will solve equations. Oh no, I think we have a review day after that, and then we'll solve the equations, and then we're done. We will be reviewing. So we're halfway through this unit already. That seems crazy, doesn't it? All right, you guys are doing awesome.